Hey everyone, my name is Max Wasserman, and I'm excited to discuss the recent TMLR paper, Stabilizing the Kumaraswamy Distribution, which I carried out with my advisor, Gonzalo Mateos at the University of Rochester. This work focuses on the Kumaraswamy distribution, an expressive, beta-like distribution well suited for latent variable modeling due to its tractability advantages and closed-form reparameterization. We identify critical numerical instabilities in its relevant distribution functions that we believe have hindered its adoption and propose a stable reparameterization grounded in modern scientific computing techniques. This fix unlocks the Kumaraswamy for scalable use in probabilistic models. We showcase its utility in several settings, including contextual multi-arm bandits, where we propose a new method, the variational bandit encoder. Here's a quick overview of today's talk. We'll begin with a brief review of latent variable models, a fundamental approach within probabilistic machine learning. Next, we'll narrow our focus to latent variable models with bounded interval supported latents, and introduce the Kumaraswamy distribution as a tractable expressive option in this setting. Then, we'll shift to contextual multi-arm bandits. We'll review two dominant approaches and introduce our proposed method, the variational bandit encoder, which combines their strengths. We'll conclude with a look at promising directions for future work. We begin with probabilistic models, where a model defines a family of distributions over data, and learning means finding parameters that best explain the observations. In fully observed models, like logistic regression or naive Bayes, all variables are observed. These models permit tractable maximum likelihood estimation of the parameters, as we can directly evaluate and optimize the likelihood. Latent variable models, abbreviated LVMs, extend this by introducing unobserved or latent variables and represent a powerful modeling approach, which enables rich likelihood construction, prior knowledge incorporation, and efficient sampling, but also introduces challenges, namely inference, computing the posterior over the latent variables, is often very difficult, and maximum likelihood-based learning is typically intractable. Latent variable models define a generative process by introducing unobserved latent variables. We specify a prior over the latent variables and a likelihood that relates the latent variables to observed data. Their product gives the joint distribution, and to assess model fit, we marginalize over the latents to obtain the marginal likelihood. The evidence, or the log marginal likelihood, is the quantity we seek to maximize in maximum likelihood estimation, but its gradient is often intractable, posing a significant obstacle to training latent variable models. Since the evidence gradient is generally intractable, we turn to variational inference. We introduce a variational distribution Q with parameters phi to approximate the true posterior. This gives a tractable lower bound on the evidence, called the elbow, which we aim to maximize. Maximizing the elbow with respect to the model parameters theta aims to improve model fit, corresponding to parameter estimation. Maximizing the elbow with respect to the variational parameters phi encourages Q to match the true posterior by minimizing the reverse scale divergence, corresponding to approximate inference. Optimizing the elbow requires computing gradients with respect to both phi and theta. But the elbow approximates involves an expectation under Q, which itself depends on phi. Estimating gradients of expectations with this form is challenging, but a well-studied problem, and we quickly review common approaches. The core challenge here is that we're taking the gradient with respect to phi of an expectation under Q, where the distribution itself depends on phi. If we naively applied Leibniz's rule to bring the gradient inside the integral, we lose the expectation form, because the gradient of Q isn't a valid probability distribution. This blocks us from using standard Monte Carlo estimators. There are two dominant approaches to recover Monte Carlo estimators of the gradient. First, the score function estimator, also known as reinforce, rewrites the gradient using the log derivative trick. It works generally, but the variance is often too high for efficient elbow optimization. Second is the reparameterization trick. If our distribution Q supports the reparameterization trick, we can express sample Z as the output of a function G with inputs epsilon and phi, where g is a differentiable and invertible function, and epsilon is noise independent of phi, often uniform or standard Gaussian. This gives us an expectation over fixed noise, enabling efficient, low variance Monte Carlo estimates of the gradient and thus efficient elbow optimization. In practice, this is the preferred approach in modern deep variational inference. With the necessary latent variable model machinery in place, we can now turn our focus to an important class of latent variable models, those with latents supported on bounded intervals. We'll also introduce the Kumaraswamy distribution, an expressive, reparameterizable distribution well suited for this setting. Many real-world applications can be modeled by latent variable models using latent variables constrained to bounded intervals. These include continuous control settings, conversion probabilities in ad ranking, mean reward estimation in bandits, and event occurrence probabilities in forecasting. This motivates the need for expressive, reparameterizable latent distributions with bounded support. When selecting a variational distribution for latents on bounded intervals, we want 4 key properties. The support of the distribution should be on the unit interval to match the posterior's domain. Note the support on the unit interval can be trivially scaled and shifted to any bounded interval. We want expressivity to capture complex posterior shapes. We want the reparameterization trick for low variance gradient estimation. And we want simple distribution functions for fast and stable evaluation. Let's look at 3 candidates. First, we have the tan-H squash Gaussian. It's reparameterizable, but limited in shape. For example, it can't represent the uniform distribution, and contains some unresolved numerical instabilities. Second, the beta distribution is expressive and well studied, but lacks the reparameterization trick. Finally, the Kumaraswamy distribution, denoted as KS, can take the same prototypical shapes as the beta, including the uniform distribution, and supports the reparameterization trick. The Kumaraswamy distribution is defined over the open unit interval and parameterized by 2 positive shape parameters, A and B. Its PDF resembles that of a beta distribution, but without the beta function normalization, making it simpler to evaluate. Crucially, the Kumaraswamy has a closed-form inverse CDF, shown here in the bottom, which allows us to reparameterize samples as a deterministic function of uniform noise, making the Kumaraswamy particularly attractive for variational inference with bounded interval-supported latents. Now, I'm not the first to point out that the Kumaraswamy is well suited for variational inference. Here's a GitHub request from Jasmine Bastings, a researcher at DeepMind, advocating for the inclusion of a stable Kumaraswamy. She says, Kumaraswamy variables are simpler to reparameterize, which is not the case for beta variables, whose techniques are complex and typically lead to higher variance. We would like to use it in our research, probably so would others. Now, leading researchers across a wide variety of domains have been publicly asking for a stable Kumaraswamy. In this GitHub thread, we see interest from researchers at the University of Amsterdam working on natural language processing, Stanford researchers working on probing large language model behavior, DeepMind researchers currently working on massive vision and diffusion models, and Sam Dalton at Meta, the creator of a popular Bayesian optimization package BoTorch and a recent author of a NeurIPS Spotlight paper. The struggle for a stable Kumaraswamy implementation spans years. Ongoing developer threads spanning back to 2018 reveal how machine learning library maintainers have struggled to implement the stable Kumaraswamy distribution, consistently hitting issues like NANs and invalid reparameterized samples. Even today, pulling the latest main branch of PyTorch or TensorFlow services the same issues. Kumaraswamy remains unstable. Let's take a closer look at the numerical issues using PyTorch's provided Kumaraswamy implementation. On the left, we plot the PDFs of several desirable Kumaraswamy distributions. The jagged, spiky curves reveal instability in the evaluation of the density. In the center, we plot the inverse CDFs used for reparameterized sampling. These two exhibit jaggedness, and past a certain point, they collapse to 0 due to underflow, meaning around 39% of inputs from the uniform distribution map to exactly 0. On the right, we see the result of the problems in the inverse CDF. The reparameterized samples form visibly quantized histograms, and around 39% of samples collapse to zero, violating the distribution support. So while the Kumaraswamy is appealing in theory, these numerical instabilities severely limit its use in practice. While inspecting the Kumaraswamy's expressions, I uncovered the hidden numerical culprit, catastrophic cancellation, which is a loss of precision when subtracting nearly equal numbers. This occurs in the term log of 1 minus the exponential of x, which becomes unstable as x approaches 0. Machler in 2012 proposed a stable alternative using widely available numerically stable primitives. The plot on the right shows the difference. The naive version in red quickly goes unstable, while Machler's version in blue maintains low error across the domain. The presence of this unstable term in the Kumaraswamy isn't obvious from its standard parameterization, but it occurs in all relevant distribution functions, namely the PDF and inverse CDF, as well as their gradients. To address the instabilities in the Kumaraswamy, we introduced two contributions. First, we reparameterized the log PDF, inverse CDF, and their gradients using unconstrained parameters log A and log B. This enables stable log space computation and isolating every instance of the unstable log of 1 minus x shown here in red. Second, with these unstable red terms isolated, we can now directly substitute in Machler's numerically stable formulation, ensuring accurate evaluation throughout. We now have an unconstrained numerically stable Kumaraswamy, well suited for scalable use in modern latent variable models. After implementing our stable Kumaraswamy in PyTorch, we can revisit the same set of Kumaraswamy distributions. In the bottom row, we see that all major issues are resolved. The PDFs are smooth and well behaved, the inverse CDFs no longer underflow, and the sample histograms now accurately reflect the continuous shape of the target distribution, no quantization artifacts, and no point mass at 0. In short, it restores the behavior modelers reasonably assume from a well-defined distribution. To validate our stabilized Kumaraswamy, we evaluate it across a diverse set of latent variable modeling tasks. Shown here are two examples. First, contextual multi-arm bandits, where it shows better exploration-exploitation trade-offs with lower regret. Second, GNN-based link prediction on standard datasets, where it improves uncertainty quantification and calibration. Shortly after posting this work to arXiv, we were excited to hear positive feedback from the community. One standout example came from an unexpected area, vector quantization for search. Data stacks leverage the unique properties of the Kumaraswamy to learn non-uniform quantization strategies, achieving a 15% improvement in compression, reducing the size of vector embeddings and yielding significant storage savings in large-scale vector search systems. Dr. Mariano Tepper, their vector search R&D lead, reached out directly, and we've since explored follow-up collaborations. And finally, we have a pull request pending to integrate the stable Kumaraswamy implementation into PyTorch's main branch. Let's now turn to contextual multi-arm bandits, a setting where decision-making under uncertainty is central. These problems appear widely in real-world systems, where from recommender systems to adaptive experimentation, where you must choose among a set of actions based on side information or context and learn from feedback over time. As we'll see, the structure of these problems makes them a natural fit for latent variable modeling, and particularly bounded interval latents like probabilities. This will set the stage for introducing our final contribution, a novel contextual bandit model called the variational bandit encoder. Multi-arm bandits model sequential decision-making, where we attempt to learn the feedback tied to our actions, unlike supervised learning with fixed data. The term multi-arm bandit comes from a classic casino analogy. You face several rigged slot machines, each with a fixed but unknown payout rate. In order to maximize winnings with a limited number of pulls, you must balance exploration, trying machines to learn their payouts, and exploitation, sticking with the one that seems best so far. At each step, you choose one of K arms and receive stochastic feedback in the form of a binary reward drawn from a Bernoulli distribution, parameterized by a fixed, unknown mean reward mu with value between 0 and 1. The presence of an unobserved mean reward value supported on bounded intervals should begin to provide hints as to how this ties into the Kumaraswamy. Now, if you knew the arm with the highest mean reward, denoted mu star, the optimal arm selection strategy or policy would be to play it every time. But since mu star is unknown, the challenge is to learn which arms are best while still collecting high reward. The standard objective is to minimize regret. In other words, the expected difference between the reward of the optimal policy and that of your own, which measures how far your policy falls short of the best fixed decision in hindsight. A natural extension of the basic bandit model is the contextual bandit. We still have k-rigged arms, each with a fixed but unknown mean reward probability, denoted mu sub k, and each binary reward is sampled IID from a Bernoulli distribution. But now, each arm also comes with an associated n-dimensional feature vector, denoted x sub I, which may carry information about the expected reward. For instance, imagine each slot machine has visible features. Maybe it's color, manufacturer, or year of production, which could contain correlations with mean rewards across arms. The challenge is to learn a policy, meaning a rule that maps from context and action reward histories, to a strategy for choosing arms, which balances exploration and exploitation to minimize regret. This is a rich and mature field, but I'll briefly highlight two broad families of approaches: the point estimator approaches and the Bayesian parameter modeling approaches. Point estimator methods posit a parametric function E with parameters theta, often a linear or neural function, that maps context vectors x to mean rewards mu. The parameters theta are estimated from observed data, typically through maximum likelihood, and are updated periodically. Arm selection is based on predicted rewards, optionally adjusting using a fixed exploration heuristic. For example, greedy methods, which always select the arms with the highest predicted mean reward and no explicit exploration; epsilon greedy methods, which act greedily with probability 1 minus epsilon and uniformly at random with probability epsilon; and UCB methods, which select the arm with the highest plausible value or the highest upper confidence bound, a sum of the estimated mean and an uncertainty term, to safely explore under worst-case assumptions. The advantages of point estimator methods include low complexity. Fitting maximum likelihood models tends to be straightforward, making these methods accessible to most practitioners, and interpretability, as the models directly output predicted mean rewards, so arm selection decisions are transparent. Disadvantages include the often poor sample efficiency and the no clear mechanism to incorporate known information about specific arms into the model parameter estimates. The limitations of point estimator approaches help motivate Bayesian approaches. The setup remains the same as in the contextual bandit case, but now we introduce a latent variable model in which the context and rewards are observed random variables. By performing inference, we obtain a posterior distribution over the unknown mean rewards, visualized in the last row. We derive a policy from this posterior distribution to balance exploration and exploitation more naturally. A common policy is Thompson sampling, which selects the arm with the highest sampled mean reward from the posterior. The traditional Bayesian approach extends point estimator methods by treating the parameters theta of the reward function E, which maps the context vectors to mean rewards, as latent random variables. In this approach, the posterior belief over the mean reward, which guides the policy, is not modeled directly. The mean reward is a derived quantity, and its posterior is induced by the posterior over model parameters. This setup has a key limitation. Because the mean reward is derived, we cannot place a prior over it, making it difficult to encode prior knowledge about specific arms. There are two primary strategies for performing inference in this setting: Monte Carlo sampling methods, like Langevin dynamics or Gibbs sampling, which aims for asymptotically exact posterior samples, or variational methods, such as Gaussian or dropout-based approximations, which trade accuracy for efficiency by approximating the posterior with a simpler, tractable distribution. These methods present certain advantages. They provide a principled, data-driven way to quantify uncertainty over mean rewards, enabling exploration through Thompson sampling. And there are some attractive regret guarantees in certain settings, for example, linear Gaussian models. They also come with distinct disadvantages. For example, Monte Carlo sampling can be prohibitively expensive, particularly for expressive models such as neural networks, due to the need to store the full dataset in memory and perform often hundreds of likelihood and gradient evaluations for each posterior sample. They can pose scaling issues. For example, online variational methods often involve operations quadratic in context vector dimension, limiting users to small context sizes. Both approaches can be sensitive to the specification of hyperparameters, often requiring expensive tuning, for example, step sizes, burn-in, or stable matrix inversion. Finally, they still have a limited ability to incorporate prior information on arms, as priors are placed on reward function parameters theta, not mean rewards. We're looking for an approach that combines the strength of both paradigms. From point estimator methods, we desire the low complexity. We would love to optimize them with just standard tools like stochastic gradient descent, no matrix inversions, or extensive hyperparameters which require tuning. We want scalability. We should have complexity linear in context dimension, dataset size, and parameter count, making it practical for modern high-dimensional applications. And we want interpretability, the ability to inspect model outputs and understand its predictions or beliefs about specific arms. From Bayesian parameter modeling, we want principled data-informed handling of mean-reward uncertainty to guide exploration-exploitation trade-offs. And ideally, we want something neither approach provides, a way to directly incorporate prior knowledge on mean arm rewards. The high-level idea of our proposed approach is to use a neural network to output an approximate posterior over mean rewards. To build this, we need to answer two questions. What should the probabilistic model be? What are the variables we want to model, and how are they related? And how do we train the neural network, E, so its output approximates the true posterior under the model? We now introduce our proposed approach, the variational bandit encoder, which we feel combines the attractive strengths of both point estimator and traditional Bayesian approaches, while combining direct incorporation of prior knowledge over specific bandit arms. The key idea in the variational bandit encoder is to introduce a latent random variable mu that explicitly represents the unknown mean rewards, enabling a prior to be placed directly over these values. Recall, this is in contrast to the traditional Bayesian methods, which models the parameters theta as a latent random variable and indirectly derives model beliefs over mean rewards. In the variational bandit encoder, we define a conditional prior over the mean reward variable mu, given the context x, which can be hand-specified, for example, specifying the parameters of a beta distribution, or learned, for example, using a neural network to encode some parametric distribution, or even a normalizing flow. We also define a reward likelihood conditioned on the mean reward variable mu. Here, we use a Bernoulli reward with mean reward supported on the unit interval, but the framework readily supports alternatives, for example, Gaussian likelihoods for linear reward models. Both the conditional prior and the reward likelihood shape the posterior distribution over the unknown mean rewards mu. With the model defined, we now introduce a variational posterior Q to approximate the true posterior over mean rewards. This approximation is parameterized by a neural network encoder E with parameters phi. Given a context vector x, the encoder outputs the parameters of the variational distribution Q, which is trained to match the true posterior. Since each mu k is supported on the bounded unit interval, we use a fully factorized Kumaraswamy distribution as the variational family. The Kumaraswamy is well suited to this setting, as it's relatively expressive, it supports the reparameterization trick, and has simple, closed-form distribution functions. But we note that the more expressive variational distributions, for example, normalizing flows, are also compatible with the VBE modeling approach and can be used if compute, sampling latency, or data scarcity are not concerns. With the model and variational posterior defined, we now turn to the training objective, the elbow, composed of a data fidelity term and a prior matching term. Since the variational posterior Q was chosen so to support the reparameterization trick, we can perform efficient optimization with respect to both the model parameters theta and the variational parameters phi, which in practice amounts to stochastic gradient descent on the elbow, typically requiring just a single forward and backward pass of a neural network. All components involved in this process are standard in modern autodiff libraries like PyTorch. Now, the key modeling decision is the form of the conditional prior. This choice should match the data regime. When there's abundant data, we can learn a flexible prior, for example, using a neural network, which takes the context vectors as input, allowing the model to interpolate prior beliefs across the feature space. With limited data and strong prior knowledge, we can use manually set priors, for example, beta distributions based on this prior knowledge. Finally, with limited data and limited prior knowledge, we can set a high entropy prior like the uniform distribution to encourage exploration. Here's how we use the VBE for Thompson sampling at each round. Denoted in red, we first pass each context vector through the neural network encoder to produce the Kumaraswamy parameters, defining the variational posterior over mean rewards. We then perform arm selection through Thompson sampling, denoted in blue, by first drawing one sample per arm from its variational posterior, and then selecting the arm with the highest sampled value. In gray, we indicate the pulling of the selected arm, the observation of the Bernoulli reward, and the recording of the context action reward triple into the replay buffer. Finally, in green, we construct the elbow from the updated buffer and take a gradient step to update both model and variational parameters. To evaluate VBEs on a standard synthetic contextual bandit task with 10,000 arms and 2,000 rounds, each arm is associated with a 5-dimensional context vector sampled from a standard normal distribution. The hidden mean reward for each arm is computed by taking the inner product with a shared weight vector, also drawn from a standard normal, and normalizing the result to the unit interval, producing a probability. We compare 3 VBE variants using different variational posteriors: the Kumaraswamy, the beta, and the Tanh Gaussian, under an exploration promoting uniform conditional prior. All achieve low regret, and the Kumaraswamy-based VBE achieving the lowest. We compare against Lange and Monte Carlo with Thompson sampling, a state-of-the-art contextual bandit approach denoted here as LMC-TS, which is performant but incurs high sampling costs. We find the VBEs are far more efficient, and the Kumaraswamy variant even outperforms LMC-TS in regret. We'll now wrap up by showing how the variational bandit encoder, VBE, can be used in the common setting of movie recommendations. Further, we'll show how the VBE's ability to incorporate prior beliefs directly over mean rewards can be used to address cold start problems. Consider the movie recommendation setting. The feedback matrix has rows representing users, each with a context vector X superscript U that may include demographic features like age, gender, viewing history, and preferred genres. Columns represent movies, each with a context vector X superscript I that can include metadata such as genre, average IMDb rating, release year, and a semantic embedding of the movie description, for example, from a pre-trained text embedding model. Each user-movie pair defines an arm, with its context vector formed by concatenating the respective user and movie context vectors. In the data-rich regime, where we have plenty of interaction data, we can allow the VBE components to be learnable. For the conditional prior, we can use a neural network to map from the user-movie context to encode, for example, a beta distribution. For the variational posterior, we can use another neural network to map from the user-movie context to encode a Kumaraswamy distribution. We optimize both by maximizing the elbow, shown above, after which we can directly inspect the model beliefs on each user-movie pair by visualizing the variational posterior. In other words, pushing the concatenated context vector through the variational posterior neural network, the encoder, and visualizing the Kumaraswamy distribution its output defines. The variational posterior tends to place low posterior probability over, for example, older men liking Frozen, but higher posterior over probabilities like Rocky, which makes sense. Now, in system cold start settings, where we have no user item interaction data, since the feedback matrix is empty, the reward likelihood term in the elbow vanishes. What remains is the KL divergence between our variational posterior and the conditional prior over mean rewards. Here's one way we could proceed. We select a representative subset of items, for example, Rocky, Frozen, and Up, and assign prior distributions based on believed audience preferences. For example, for the movie Rocky, we may specify a beta distribution with significant probability mass over high mean rewards for older men, reflecting our prior belief that this demographic will find this movie appealing. Whereas for older women, we may assign a beta distribution with probability mass shifted down to relatively lower mean reward values, reflecting our reduced confidence in this movie's appeal to this demographic. These priors encoded a priori beliefs over user item affinity. Now, the VBE's Kumaraswamy variational posterior Q is parameterized by a neural network taking in the concatenated user and item features. And so we can efficiently optimize the elbow using stochastic gradient descent, minimizing the KL divergence between the variational posterior and these manually specified priors. Doing so, we expect the network to interpolate our prior beliefs across feature space, yielding meaningful estimates of reward probabilities in regions with no hand-specified priors. This enables a principled, warm start across the entire system, allowing the model to make informed recommendations before any interaction data has been collected. Now, let's turn to item cold start, when a new item is added to the system without any interaction data. In systems with rich interaction data, new items can be handled by generalizing from item features. If a new movie resembles others with high rewards, the model can infer high expected reward for users who favored similar items. But if the item is very niche, dissimilar from all other items, and we have strong prior beliefs, for example that certain demographics are likely to enjoy the new movie, we can do better. Just like in the system cold start, we can assign prior distributions per demographic, reflecting our beliefs about who this item is for. These priors help guide the model's behavior before any interaction is collected, allowing it to make informed early recommendations for brand new items. Maximizing the elbow and visualizing the posterior model beliefs again shows how our prior beliefs can propagate to inform the posterior. We can address user cold start, in other words, when a new user is added to the system without any interaction data, in a similar way to the system cold start. On a representative subset of items, for example, Rocky, Frozen, Casablanca, we assign prior distributions based on our believed audience preferences for the new user's demographic. For example, we believe it unlikely a young female will like Rocky or Casablanca, but likely that she will enjoy Frozen. And again, maximizing the elbow and visualizing the posterior model beliefs shows how our prior beliefs can propagate to inform the posterior. Finally, we address some promising directions for future work. The VBE was introduced as only one part of the Stabilizing the Kumaraswamy TMLR paper, but it warrants deeper evaluation, particularly on real datasets. It's especially well suited for settings with high dimensional arm features, significant prior knowledge on expected rewards, and sparse interaction data. For example, on mobile app stores, where users may only engage with a few items per year. To enable broader adoption, especially in critical applications, it is important to establish theoretical guarantees, such as asymptotic optimality, ensuring that the policy converges to an optimal behavior over time, and regret bounds, quantifying how quickly the algorithm approaches optimal performance, typically in terms of cumulative regret. If you have any questions, feedback, or a great multi-arm banded application where you think the VBE would be a great fit, I'd love to hear from you, and feel free to reach out.